Okay, yes. But you get it nice. And try to close it off early.
What is the slide about?
I don't need to see this.
Oh, so the best way is to just sit and be surprised.
Brendan. Mary.
We were waiting for those HCST folks to arrive.
But we're here. They can start.
I see usually committee that's over here, like on the far side, away toward the front.
Can you see the grid?
Appreciate the hotels and literally
Yeah, exactly.
But I came out a couple of Kinetic.
That's interesting, you know.
Yeah. Gonna be the next 5 to 7 years.
When to start?
2 years from now. After 4 years. 4 years.
We can get started now. Everybody wants to get to the happy hour for the beer, so. All right. My name is Panther. I'm the chair of the storage committee. I'm very happy today to have Christian giving us a presentation from Seagate. For those who don't know, I'm working for Seagate as well. This is the very first time actually that this topic will be presented by Christian. It's the product name is Cloud Gazer, and I think you will really enjoy the presentation and the depth of the topic. So with that, I give you.
All right, thank you. You all hear me in the back? Great. So I think the overall messaging of what I'm talking about here, which is agreeing to lower the total cost of ownership in a data center, is really in tune with what we heard at the keynote session today, that there are operation costs where a lot of reduction can happen. And the point of the first part of this title is really the way we want to accomplish this is by health monitoring and predictive analytics. And so let's jump right into it. Here's an outline I'm going to talk. First, I'll try to outline the opportunity a little bit more, and then I'll jump into our vision and implementation. When we see this opportunity and how we think we can help with it. And then it's not just going to be presentation and theory. I'll show you use cases. This technology user that Aspen referred to is already existing, and so I'll show you some examples of what it looks like. And then finally, I'll summarize and allow time for questions if you have any at the end of the talk. So, what is the opportunity? How can we lower the total cost of ownership? What if Seagate offered you a technology that could help you improve data center efficiency and optimize system management and finally reduce potentially the cost of operation? Some of you may work in or with data centers, and you may have a pain point around the efficiency that you're familiar with, or the other bullet point is some of you might just see cost reduction, cost reduction, cost reduction. It doesn't matter too much. I just want your attention at this point by saying that we believe we can help you save money. And how's that? Well, as you might have guessed, since I'm with CData, it's because there's a storage-related problem. And I'm going to outline it in maybe a couple of different ways here, but let's start with the pie chart on the left. So what that shows are that we'll have billions of drives in 2020. But what's even more interesting is that over half of those drives will be in the cloud. And that really highlights the need to manage drives at scale. It highlights that there'll probably be a pain point, and we believe this because it will not only be the big players, the tier 1 cloud service providers that will help provide your cloud, it'll also be cloud service providers that first had 5,000 drives, then 10,000 drives, then 30,000 drives, and they don't have the history or the time to figure out necessarily how to manage drives at a scale. And so it'll be painful. It already is a little bit, and I'm trying to highlight that with the rest of the slides. So on average, there is one outage per data center per year. And 80% of those outages are not completely explained, but either way, they're very expensive. The average cost is around $700,000 or $8,000 per minute. Now, at least 10% of those accidents are related to storage. Now, granted, there's a lot that's not explained, so there's a high need already as things are today, and with the price out there for more visibility and for a way to handle this. We went out and we talked to customers and partners about what do you think, how do you think we can help with this issue. Basically, we arrived at 4 top challenges in drive management at the cloud data center level. So the first one was simply drive health monitoring. Okay, we need reliable key performance indicators to track the drive health status, and that means that you, for instance, it's not enough just to look at smart and look at thresholds. Those are dependent on drives and saturations. They're not general. And that links directly into the topic of drive failure prediction, which was most people's favorite topic. Basically, here's a quote: ultimately, we want to know when our drives will fail so that we can take actions before that happens. And there's a couple of reasons for that. One is it's just nice to know now I'm going to have a big fraction of drives fail, so you can have your replacements and you can be ready to take action. But there's another very important factor here, and that is if you're running a data center, even if you have something like Swift running with many copies, if you have substantial drive failure, all of a sudden you're going to have to back up that data somewhere else. While you may not lose data, well, you're going to put a lot of stress on the drives to back up that data, and you may be flooding your network. But if there's a way for you to predict that you're about to come into a bad situation, you have some time to deal with that. The third point is drive failure diagnostics and management automation. And so we wanted to help, and what we were told we could help with was to correctly identify and quickly resolve issues. So one of the big things that cost a lot of money is false failures. And sometimes that's evident on-site just by swapping drives to make things work. And for us, it's evident at Seagate because we get some drives that are not failures. And no one wants the false failures. It's who wants to not use a drive that's actually usable. And then the fourth point was drive lifespan extension. So there are 2 sides to that topic. One is we at Seagate believe we can help you optimize your environment for, well, basically, the moral of the story is we want to help you optimize how you use your drive by guiding you as to how you use your environment. And I'll talk more about that in the use cases. And then we may be able to provide technologies that allow you to use partially good drives. So I'll show an example of how CloudGazer right now offers in-drive diagnostic. And if you're not familiar with it, but you're familiar with drive subtests, somewhat similar, except that there's drives that are going on and you literally which can be really helpful for identifying and dealing with false failures. So now to talk about this, there's a storage pain point, and that storage pain point will be even bigger in 2020, and we can help with it because storage is the thing we do. So let me jump into our vision and our implementation. How do we help data centers reduce the cost. Okay, and I have 3 slides trying to outline the implementation. So here's the very high-level slide, and it all starts in the middle. And I call this slide the Internet of Things squared. Let me try and explain why. So we're all familiar with the notion of the Internet of Things. Our devices can report back, and we're hoping we can use all the data to make smarter decisions, to get better service. Well, usually that data has to be processed by a manufacturer or somewhere in the cloud. And that's what I show in the middle. It's the cloud, it's the data center. And basically with CloudGazer, we're suggesting a similar technology to improve the way the cloud runs. That's where the Internet of Things, where it comes from. So it all starts with monitoring. We're going to monitor what goes on, and most of the stuff in the data center is storage, the drives. And that's our focus. And then, of course, we're going to store historic data over time, and then based on the data we have, we can do analytics. Now, one point I want to make before I go to the analytics is there's, as we see it, a need for global access to this data. Someone needs to be able to grab the cell phone and figure out what's going on and be able to make decisions from there. So we need global access. So then we go to analytics. We need to do analytics, which could be as simple as throwing off an alert that will say, hey, we need to replace a drive. But even more important are the predictions that say, hey, in X months, you're going to need to expand your storage pool because you're going to run out of storage. Or, hey, in 9 days, you're going to have all other drives fail. You want to do something about it. To a certain extent, we can even offer control within this whole CloudGazer framework. So, for instance, let's say that we see issues with the drive, we can automatically run drive self-tests and try to restart the drive. And if the drive is just not responding, well, we can do an in-situation failure analysis. So, in short, the components we're proposing are drive-centric health monitoring, because that's kind of the lowest level in the data center. And then analytics and predictive models, and that can go into closed loop automation. I have a functional diagram on the next slide that explains it, and it's a little simpler there. Basically, let's start on the right. We're basically monitoring if everything's in compliance, and if it is, we just keep monitoring. And if it's not, we're going to have to throw an exception, an alert, along with some recommended actions. That depends on what you're monitoring. And you can choose between some actions, and you get resolution, and you just keep monitoring. Okay. So let's look at a specific example. We're monitoring drives for drive health. And if it passes, we're happy, but maybe at some point the drive is not passing, it's predicted to fail. Well, you may want to, at that point, for instance, reset or turn off the drives. There are a couple of other options. I just listed a few here. So maybe your action is to turn off the drive. That could be the case if, for instance, you're running Swift. If you are knowing that you'll have a backup copy and you can always go in after the fact and replace the drive at your convenience. Once we tie into either a specific storage application, or if we allow the user to save the settings, most of this flow can actually be automated. But it's just a little dependent on the situation, so I didn't want to generalize it too much. Getting a little bit more specifically into the components of CloudGazer, if we look at the top first, we have our data center basically to the left, and you have all your drives in the storage centers, and what we're doing are we're running agents on each of the storage servers, collecting important metrics. And all the metrics are then processed by an analytics engine that stores all the important data in a NoSQL database. We use NoSQL just for scalability, because you need to be able to monitor tens of thousands of drives. Although relational databases have their strengths, there are limitations when we monitor all these drives, and not only drives, but also the context of the servers and clusters to evaluate what's going on. Now, this database, I was talking about global access, and so it can live either locally on-premise in a data center or in principle in a cloud. It's not tied to a specific location. It can be accessed via a RESTful API. So you can query data, you can check for thresholds, you can even send commands to manage your drives. And I'll show you an example of how we use that REST API to build up a dashboard. You'll see some slides in the use cases, but it could also be a storage software, Swift, Clever State Stability, something else that was talking to the REST API. And I'll try and explain below here why that might be interesting. Because you have your storage software kind of sitting in the top from a drive perspective at least, and it's just monitoring copies, and it's just monitoring, can I read, can I write, do I have problems? Well, we want to squeeze in the cloud-based technology between that and the actual drives, because we're monitoring the metal, if you will, directly. And we have predictive algorithms so that we can tell the storage software, hey, you know, drive A, B, C are going to fail, and you can let the storage software decide if it's a big problem or if user X actually has data out of places and you don't need to do anything right now. And finally, you can also access the cloud-based dashboard that way if you need to go back. I'll show you some examples of how the tool can be used to provide a better visibility into the drive. They help you triage systemic issues in your environment. So let's jump into the use cases. So I was talking about compliance, and I put thresholds here. I want to emphasize that it's much more than thresholds, and I'll get to that later. But basically, if you look at your left, these are a couple of screenshots from our cloud-based dashboard. And on the left, you see basically the type of warnings you have. So that could be a price of predicted fail. It could be warnings on capacity utilization. If you have overloaded drives, if the read-write rate is too high, or if you have overheated drives. So in this case, there are a couple of dials that are red, which means that you have warnings. One of them are, well, the drives are exceeding their design limits in terms of their workload rate. And along with that comes the recommended action. So in this case, we encourage you to check out the workload statistics page, and I'll give you an example of why we recommend that on the next slide. I've hidden already here the warning for the overheated drives, but you know, naturally we would just recommend trying to see if you can cool them down somehow. Now, both overheated drives and overloaded drives are actually feeding into a real-time reliability prediction that's also shown in the dashboard, and the screenshot is the one on your right here. So basically, with the drives that are shown in this example, the annual projected annual failure rate is 0.7%. So let's just say we have 10,000 drives. We'd expect from the spec values you have 70 drives fail per year. Well, based on this real-time data we're gathering, we can actually give you an in situ updated projection. And in this case, the data center is not generally being stressed much, and so the annual projected failure rate is even lower, it's 1%, or just 10 drives a year. But as the workload, as the temperature, and so on changes, you might put the drives into accelerated failure modes, and we can give you a heads up. We've actually seen how the blue, the current failure rate has moved to the right and past the spec values. And at that point, you have a cursor saying, hey, something bad's going to happen. And it's still before the drives fail, so you can adjust your behavior and bring back down the failure rate that way. If you keep up bad behavior, well, then some drives are going to fail. And that's what the failing drive tile is for. It will just not only tell you the drives are failing, it's actually running a machine learning method that's trying to predict the drives are going to fail. And there are a couple of boundary conditions we set for this algorithm. One is universality. So we need this algorithm to work on legacy drives, on future drives in different environments. And the other boundary condition is maximum lead time, which right now is 9 to 10 days. I'll talk more about the failure prediction in a later slide, so I'll leave that here today for now, with just saying that it needs to be very general. So first, let's jump into the workloads. On the last slide, I showed that we had some overloaded drives, and the user is encouraged to visit this page. So again, a couple of screenshots from the content on the page, and if you focus on the before scenario on the left, what you see is a number of heat maps on your day, week, and month perspective. And you may be able to make out the tiny squares that are blue or red and a few are yellow. Each of those small squares represent a drive in a cluster. This is a object storage cluster that was being run with a partner. And you see that some of the servers each are some lines of servers. Some of the servers have a lot of drives. Those are the storage servers, and some servers have just a few drives. Those are the proxy servers. So what you should also know is that blue means that the workload rate for the drive is low, and red means that it's a high workload rate. Yellow actually means it's above range. So when we started this use case or this project with a partner, it looked pretty good just when we looked at the daily average. You can see on the day heat map that you have some drives working and they're kind of spread out all over the cluster. But then after a week, we started seeing that one line corresponding to one server was taking more and more workload. Those drives are starting to that even a few of them are above the workload range. And then over the course of a month, you have one server just taking all the workload, basically, way above space. That was a concern for us. And even more from the workload page, you can actually get a breakdown of what does my workload look like over time, and you can compare different calendar days. So on your left in the lower graph, you can see that there's a couple of days picked on 2 calendars. And the blue one is a Sunday, and you'll see right after midnight it peaks and then it goes flat, and the red one is a Monday we picked, and it's all flat. And you see this persistently over the month. The workload peaked on Sunday, got flat, and then flat all the other weekdays. So there were 2 problems we saw here. One was that the drives were just totally utilized. We have all these drives, and just a few of them are being used. Furthermore, it's not just utilizing some of the drives, not all of them. They were also not really fully utilized over time, just on Sunday right after midnight. The second aspect is really important too, because what traditionally would happen here is someone would be having this cluster running these drives, and at some point, the drives that are all yellow in the graph up there would fail, and it'll be returned to CDA, and CDA would say, hey, you run these drives way too hard for the kind of drives they are. And if you were the data center, you'd probably say, that can't be the case. I have this many drives, and this is my total workload, so it doesn't really make sense. And we'd all be confused. But with the visibility given here, we could talk with our partner and say, hey, you have a problem, and these drives might fail. And they could immediately see that they were hitting just a few drives. Turned out that a software reconfiguration changed the scenario from the force scenario to the after scenario. Where now, if you look at the top here, over the course of the day, you see some drives being used, but once you average over a week and a month, it's hard to make the drives, tell the drives apart because they have very similar colors. Even over time, the workloads are very similar. These graphs are very flat. So that's why we encourage someone to look at this workload page when they have drives that are overloaded, because it affects the reliability, but B, there can be something as simple as software reconfiguration that can fix that issue. So let me move on now to drive failures. So once the failures happen. As I mentioned already, we have a tile on our dashboard that says failing drives. And what we put in there is a very sophisticated proprietary algorithm where we're trying to universally see if drives are failing. Now, we just look at an individual drive at a time. We don't actually need thousands of drives to make up our decision, and we feed all the important data that we know is there into our algorithm, and it'll make a call at any point in time to say if the drive is at risk of failing. And I can't tell you too much about the algorithm, but I do want to give you a few results. So as I already mentioned, we have on the order 9 to 12 days lead time. I'll speak a little more to that later. The accuracy range is between 55 and 90%. So we'll predict at worst more than half of the failures you're going to have, which if you have a really bad situation where you have a lot of failures, that's probably still going to help you a whole lot. One of the things we want to avoid is to tell you that the drives that are not failing are going to fail, because that just is costly. You end up replacing the drives. So again, here I show a map of a cluster, and each square is a drive. It's actually from a drive management page. So what you can do is you can select drives, and you can actually schedule centrally or from your cell phone drive self-tests, or in drive diagnostic that I already talked a little about. You can even turn off drives if that's what you want to do from here. The green drives are drives that are good. The black drives are drives that are not responding. That doesn't mean that they're necessarily failing. It just means for some reason they're not reporting back. And then the red drives are drives that are pretty fail. I wanted to show this not only to show that you can centrally issue various management commands to the drives, but also because in this case, when we were doing this study, we saw 5 failures, and there was something systemic in those failures. 3 of the drives all sit in the same location of the servers, again, each server outline is the server. And so we immediately said, what could be the cause? Could it be the workload? Turned out not to be the workload. Could it be rotation, vibration? CloudGazer can give you all of those answers. And the result was a little bit surprising, although not completely unknown. It was actually the temperature, that it wasn't overheating. If you look at the rightmost line here, all the green drives are drives that are a bit lower temperature range. Drives are running cooler, and we saw a predominant failure. 3 out of the 5 drives actually sitting there, so we asked our partner to increase the temperature, and we actually haven't seen failures in the system since. I should make the disclaimer that the highest temperature in this system wasn't very high, so there was no risk of overheating. Okay. I just wanted to say a little bit about the lead time. I've been saying a couple of times now we go for maximal lead time when we predict failures. What that means is a little different from case to case, from drive to drive, from environment to environment. We have a really nice case study one I wanted to show where it's a pretty clean lead time. 12 days prior to failure, we say 118 of the drives are going to fail, so time 0 here corresponds to the time of failure. That's pretty clean, but in case study 2, it's a little more of a blurry picture because we kind of predict drive failures at a range of 23 days prior to failure all the way to 1 day prior to failure. So when I say 9 to 10 days on average, it is an average number, and sometimes very close to being 9 to 10 days, but sometimes you kind of get a range. Ideally, we'd like to aim for at least 3 days for all scenarios. And again, we currently catch 55 to 90% of all failures ahead of time. That number can be improved, and many of you probably are familiar with various studies using, for instance, supervised methods where you get very high accuracy. But again, those are very tuned machine learning techniques that focus on one environment and one class of data. So with that, I want to get to my summary. So I talked about our new technology, CloudGazer technology, and the short summary is we really want data centers, want to help data centers manage drives at a scale. And so it's a truly drive-centric tool. And also, there are a lot of ways that you can try and get information from drives that is free. But part of the agent that I showed is getting data from drives. And if you're running it in a data center, you want to be really careful because it might be running in production, so you don't want to be doing any harmful stuff with drives, and you don't want it to have any significant overhead. And so we've been very careful in constructing the application to get that information. And in general, we need agents that run with very little overhead, so I just said less than 1%. Basically, it means you can detect it's running. Right now, it's a technology that works on Linux. We're working on Windows compatibility. And then I also made the point in the talk that you can either store all the data locally on premise and get all the information there, or you can actually store it in the cloud. There's nothing about this architecture that dictates it has to be one way or the other. I said that we had a REST API, and I made the point that maybe you want this technology to be talking to your storage software. Another situation could be that you have a management tool and you want a single pane of glass, and so you want to tie all the data, all the alerts into that single pane of glass. Should also point out, I talked a lot about our drive failure prediction algorithm. At least we're talking for 30 minutes, and so we actually have a number of data scientists working on these algorithms, and it's really going beyond the traditional smart and thresholds, and we found that that's key to getting something that's universal and trustworthy. And then finally, I made the point that we can support in-drive diagnostics, but we're trying to always tie the newest OCP drives into this technology so that you can centrally, from your REST API, from the dashboard, issue commands. And finally, we're actually also right now working on extending this enclosure management, because what if your drive is not failing or not having an issue? Well, then there's the question of what is the connection. So with that, I just wanted to leave a bit of time for questions.
Yeah. So if you have any questions, please raise your hand. And here.
Yeah, I'm just curious, if you change the number on your hard drive to SSD, what's your failure rate and prediction?
Right, so we have not, right now it's HDD centric, so we have actually not tested the algorithm on SSDs.
So very incredible work. About false detection rate, I don't see any numbers. So
No, we have very low rates. General number is less than 1%, but generally it's significantly lower than that. Shoot me an email and we can certainly pick up that conversation. It's a very important number, so it's driving back and forth.
So thanks for the result. A few things, right? So I assume when you monitor. Okay, I'm from Baidu. Okay. So first, when you monitor and measure sensors, do you also monitor temporary errors, say medium error, those kind of small errors, but not resulting in IO error? Maybe a few tries fine. That's the monitor side. And when you report a failure, what kind of failure? Because failure could be temporary failure and longer term permanent failure. It could be particular sector, or it could be whole drive failure.
Sure.
So can you clarify those two things?
So I understand the question, and really what we tried to do developing this technology was A, to look at what we know from an empirical point of view about the device, but also B, to take a new approach. And so when we try to, our proprietary algorithm on drive failure prediction, we're trying not to put bias into or too many assumptions into what type of failure it is, because then there'll be legacy stuff we can't catch or stuff in the future we can't catch. So we're really not programming specific failure modes.
So concerning the proprietary nature of that, A, are you planning to open it up to us to be able to run in our data centers? And B, are you planning to open it up to WD, HCST, et cetera, so that we can have one tool that works for everyone?
You know, that's a great question. I cannot answer it, but shoot me an email and I'll put you in touch with the right person.
Hi. If the dashboard indicates that the drive is going to fail, is that a good enough return reason for the data center to go ahead and you know what, I'm going to pull this, that's going to fail?
Again, I'm just an engineer, so you know, I have to point it.
So maybe explain the work process. The prediction says as well that you have the follow-up actions that you need to go through the diagnostic tests to see if the drive really failed, because we know a lot of drives really are false failing, and that's what we're trying to prevent, right? So that's another advantage of the software, that it would give you the suggestive prescriptive action that you can follow up as an administrator, or you can build it into your software to take that follow-up step. So we can make sure that these are not false failures, these are true failures that you should feel safe to pull out or offline it. But as a company, this does not play into our warranty side of this, if that's what you are alluding to.
So one last question. No?
I'm Bill from Intel. Seems to me you could use this to balance activity just like an SSD does. I mean that's ultimately And the errors aren't manufacturing defects, it is usage based, balance the usage dynamically, and extend the life of the whole disk array.
It definitely is an interesting application. I think it depends. So I showed that slide on the storage ecosystem, and so we're really trying here to help with the drive management, and you could make the case that load balancing your drives could be part of your drive management, but right now you might have some storage application here that does that too. So we're trying to not do that at this point. Just say the drives are good or bad, if they're overloaded or not overloaded, give the information somewhere else and let that somewhere else also. But yes, it's true, you can use the information for that.
All right, thank you very much, Kristen. So next, I would like to invite Mike down from Facebook to present.
Okay, so after we set up the computer, I do a brief sort of instruction of myself. So during the past 3 years, I opened Facebook, led the open world storage design, and also cold storage hard system design. And for the past 1.5 years, and I'm working on the microserver into a box with open world, change that from JBoss to a storage server. And I gave a short presentation last year in the summit, and today I will put the update of the project status of the Panther and the Panther class.
Right, that's okay? No. Turn it off.
Yeah.
Probably okay.
So the journalist to the first give an overview of these 2 projects, and the detailed portion. First is the Panther Plus, the microserver card and its physics, and then I will get into some of the individual design considerations, some of the hardware level or system configuration, and then I will give a project status update, and then issue the OCP configuration. And the overview, the goal is to change the NUCs for the open world storage from JBoss to storage server. And NUCs is this guy. It's a true storage, and when you use it, you need to pair with the OCP server. That extra space and cost. For some of the lightweight application, such as the photo storage or any kind of object storage, you don't need that powerful server. So we put a microserver card here into the NUCs, and this now is the storage server. And it's lightweight, it's efficient, it's compact, it increases the density. So those all of these lead to cost saving. And in this design, we follow the OCP or the physical design principle. We did modular design, to max flexibility, and the backward or forward. Now, how we do this? So this is a standard board in Mars, which in this, actually this portion is right in the top portion, almost the same as standard board. And in this portion, we add all the server components, the SAS IOC, the BMC, the memory card, and this Microsoft card. So which integrates with each server to these 4 boards and configuration. And I will go into some detail of the Panther plus microserver card. So this card is the implementation of the OCP microserver version 0.7 in the interface spec. And we are seeing many cards now other than physical cards. You can check with the AMD Seattle or with the NPM. We also have this kind of card. And it's a PCI add-on card, like form factor. It has all the key elements on compute node on board. The CPU, memory, drive, and it has a second drive for cache purpose. And from the golden finger of this card, we have the PCIe, USB, large, SoC, and the Unity image that provides the interface to the system. Our card, the Panther card here, is Intel Atom or 8 SoC. It makes something less than 40 watts. And now this card developed at 2 DMOs. So a lot of questions around why we have 2 local cards here. So the purpose here is that for one of them, you can use for the OS or the local lock or the system. And the other one, you use for cache or so far we use for the photo index. To separate the OS from the data that give you better state or reliability. And for this M.2, we also have a one option to change from SATA to PCIe interface that provide even better performance. And this is the first time we are using the consumer commodity here, the M.2 or the SATA. So it brings some of the issue because it very fast. Oh, they have there, so we need more efforts to coordinate with other systems such as the firmware upgrade or configuration change. We need to quantify these parts. And here we have several configurations of this card. So the high performance configuration, we use the 8-core CPU, and 4 SoC is fully populated. So 1 and 1.2. This one is developed by WeWin and using our honey badger. I will talk a little later. So for honey badger we use for photo storage, and for future we can use for disaggregated storage mode. For the medium configuration, we built with the Quanta, it's 4 cores. And for all of the SoC slots, they actually only populate 1. And no M.2 only in SATA. So this one actually uses the weight in the TOR switch. And also, it is used in the 6-pack. So weight and 6-pack share the same origin. For the 9 card, we also use it in the fabric card. We also built a very low performance configuration that comes with the 2 cores and very limited SoC and SATA. It can be used for the monitor power monitoring purposes. We built this to image quality and we for some reasons, and we just turned it. But it's already on the corner side. So those are the Panther cards, the microserver card. So let's go back to the home badger. So why we are doing this is because the density or the intensity. So the first reason is that for the PCI, our photo storage with the server has to use the IV reach. That actually after 1 or 2 months, the photo gets clearer. So the CPU utilization rate is only, I think it's only 15% of computing one bit. So that's a waste of the cost of the computing power and within the space, extra space there. So the server take 1/3 extra space, right? And even you configure, because the configuration of the server to the JBoss, you have the fixed ratio. So the rack IT equipment, so you cannot fully utilize it. Sometimes you get waste. And we do see a lot of increasing commands for the warm or cool data, for the speed, a lot of unstructured data. So, and how we do that? When we do this, we do think about the backward compatible because the Hunter baseboard is kind of light, but the S-Lux is sustainable, S-Lux kind of narrow. So when you want the new system can accept both of these one. So then that gives you the flexibility to configure your system. I have configured this case in the last slides. So here we do some thing on the mechanical side. We short the central card guide. When you plug in the Nox LTD, then in the very beginning you don't have the guide. The right side is a bit hard, but still can find its way. And with this wide unmeasured baseball, we have a notch here that to avoid the conflict to the card guide. So by doing this, you can do this new trick with either the handle or the extender. So, yes. And another new change on the hardware side is the drive pin board. The original Nox has some signal integrity marginal concern for the SATA 60. We know that SATA drive, especially the cloud SATA drive, is coming more and more. So we want to get more margin for the SATA 60. So by doing the low loss PCB, we actually get a much more wider eye opening. So this is for the slot hard disk 9 and 14. For those 3 and 4, we have the substrate driver on the substrate extender. So if you're interested in the measurement side, you can focus on later for some details. And there are some other things to know. That when Nox, when you pull out the tray, you can actually access the cable, power cable connector in a very rear side. Just give this the top tray of the just expander. We will very seldom do this, but in some extreme corner cases, some bad drive cause the whole tray 12 volts match or power off. In that case, you need to unplug the connector and plug it back again to bring the 12 volt. But with the honey badger, you cannot, because it stretched out too much, you cannot access that one. So in this corner, we actually bring back the power button. I push this button twice, you can get the tray off and on power again. So waiting for something from here, a lot of feedback from the community or from the users or other players. So we made this change. And from our architecture side, what's changed with this from the interface server Nox to this architecture? So the first thing changed is the CPU computing capability. So the avatar is item compared to the Xeon side, the spec drops a lot. The original one is 250, and now it's less than 100. So definitely you lose a lot of computing power. But in those applications you don't need, actually it's still slightly higher than 1/3 of that. So in case you can bear with this, it's a very good choice. And we tested the haystack for the storage with this handler. So for all the 3 main access patterns, the read-only, the read-write, or the sequential operation, we get very similar results compared to the Nox combination. And the total amount of memory also dropped a lot. The original, first you can have 64 some configuration but now we have 32. So the big challenge in this project is the fault of the index. The index is more than 100 gig in the memory. We don't have some memory, we must application to do the multiplication, and they do the total index in the data to SSD. So the first, when you first load this one, it takes slightly longer, maybe from 5 minutes to 8 minutes to build all the index. But here you get another benefit when you do the power cycle. In the original one, you need to reduce that in your memory, but now it's already in the index. You can do incremental update. This saves a lot of manipulation. We want to keep the same. We do the server, storage server, and also kind of server. We want to keep almost the same thing for the original one, that the convenience or easy to deployment. So we keep the same depth or directed at the storage architecture, still the CPU and the HBA and the local storage. And here we also adopted the same DMC chip that currently is used in our data server, and also this chip is also in our weight. So from our monitoring side, they look this storage server or the big server or the switch. It looks almost the same because they are the same things, the similar commands and the similar features there. And we also keep the same OCP measuring card, the technical measuring card for which we use. And due to the mechanical interference, here we only support single port on this storage. And we also can accept the 40 gig, the coming 40 gig or 50 gig measuring card. And we also keep the same OCP debugger card. So this card has to also use the in-house or in the field. We can drive the post code from the server side, and with the slide switch, we also can see the error code and see the same thing from the logs. Here I give you some typical use cases. So we tested this use case for our deployment. It's the top tree is 100 measure with the Panther class. The lower tree is Nox STD. So we call this case 1 to 30 because one hand node handle the 30 drives. And in the spec, currently under IC review on the open website, I also give last chapter I gave the different use cases as an example for the comment from the community and some of the users. So it's possible for you to do the 1 to 15, that means each trade you have 100 plus, or you can do some cascading, such as the one high measure that you connect 60 drives, or you can go to 4 layers of cascading, so you can get 120 hard disk drive. But this use case we haven't tested, so you will need to test it with either your solution provider or the. And brief status updates of projects. So for the Panther class itself, in a way, it already mass production. In 6 packages routine. And for the rack and the power monitoring, we hold up the DVT. And for 100 measure itself, in the very beginning, we have the storage solution from both local LSI and the PNP server. After DVT, due to the resource and the strategic contribution, we didn't move forward with PNC. But the PNC solution is built by win-win. They already have some kind of readiness we want to pick up. And we only test the feature model in the 100 measure, that is 8 cores. So how the 4 cores one will handle the test, we didn't do. But the 4 cores from outside is in the weight 6x3. And we only test on the disease. And we also in PG, we test the cloud drive. And basically, can use something more monitoring or health prediction, or the kind of things with that cloud drive. We believe that this will be a trend, but we are still in very early stage to put it in. And for 100 measure itself, it's in PVP, and we are going to move to pilot and mass production. So we need to now to. And for the OCP contribution, so we contribute 2 specifications. One is the 100 measure, the entire storage server, and also the Panther Plus as the integrated project. Panther Plus also has its spec. And the new contribution here start from here. We collect with the ODM, and the ODM, QDM will contribute the full design package on their own. We put the requirements, we review their package, we make sure that the package complete for other users to adopt or to study. So we will contribute the honey badger. We will contribute the honey badger in the package and the quantum contribute the Panther plus. Actually, we will already submit that to committee to IC for review now. It could be available within 1 or 2 weeks. And what the full design packaging is, that means in the mechanical side, you will have all of the 3D files, 2D drawings, and the form of all the stimulus that you can actually, there's the source code, so you can use it for any purpose for any modification. And in the electrical side, you have the schematics, not only PDF, but also the original DSM in the vehicle, and in the canvas. The layout all file in vehicle, and also the cover file and manufacturing side, and also the BOM. The BOM actually comes with the vendor and the panel of each component. So you get every detail for the design. So that ends my presentation. So contact me in my channel, Facebook, or the email, or you can visit us on the OCP booth.
So, any questions?
So what is the typical cost for Panther and honey badger?
Yeah, that's a very good question. I don't think we can disclose any kind of actual cost. I can tell you that for the Panther Plus itself, if the Panther Plus and the honey badger together to replace the Winterfell, it's the Winterfell and the OCP, the total, I think it's less than 40% or even just 1/3 of the cost.
Right, you have the BOM there so people can look up those costs and come up with it.
Yeah, the BOM, you can do the estimation of the cost of the component highly depends on your volume. So you can do estimation on your own, but if other customers take the same price.
So all of these are single linked, right? The drive. There's no dual path.
That's correct.
And there's a plan to build any redundant controller, redundant server module.
No, first is due to the mechanical or the dimension constraint, and then the other one we believe that for moving forward, the SATA drive will, if it's take one more, such as the cloud drive or the SSD. So we think on the drive side, it's okay to just keep a single port. And if we talk about the high level architecture, scale out is always the clustering. So we don't think we actually here in this kind of community.
So any of those are in production based
The Panther Plus version in the weight is already production. This honey badger as a total, we're going to production within 4 months. We are about to go to the pilot production, pilot machine. So we ramp up gradually.
Thank you for the great submission. On the 1 to 120 ratio, is it specified that it only can go in a single power zone rack, or is there any way to make sure that we're not splitting the head node from the tail nodes at different power zones?
Yeah, that's a good question. So I don't think if in V2, in override V2, so I think we can hold it within one power zone. Yeah.
Right, in V2 rack,
But
there should be some way to say you can't put it in a V1 rack, only in a cold rack or V2.
Yeah, I think we're better to do that for C.
Great, and thanks for getting the third versions one out. That's wonderful.
Yeah.
Earlier you mentioned the M.2. Is that PCIe or SATA?
Yeah, so far what we are using is on SATA interface. on this PCB design, because the SATA and the PCIe, they share one of the same port, same lane. So we have to do the bomb population. That means you pop some of the resistor and add some of the resistor there. So the board itself can support the PCIe. And actually, the backend, I tested the PCIe, every work that tested the PCIe works.
Thank you. Any other questions?
My question is about serviceability. I've seen in the booths a few vendors have this already, and the 15 drive on one U and the other 15 on another. They seem, if one drive fails, it seems first there is no LED indicating whiches, and second is you have to unplug the whole tray, which is unplugging the power for 15 drive together. Do you see a problem? Do you see improvement on the road?
Actually, if you are familiar with the Knox already, the Knox is hot pluggable. So if you pull out the tray, it has a power and signal cable and cable connector. And just now, can still get connected. So in the front, you still have the mini-size cable. So you need to take care of the cables, but it's actually hot pluggable. So also for the 100 beta, we support the same. And also regarding your question, what the hard drive is doing? With this debug card, you plug into the debug header, it actually shows some of the Knox code, Knox error code. Maybe 53 in this slot 3 has smart error. So we have those in the Knox or open water spec already.
One last question? No? All right, thank you very much, Mike. So thank you very much for holding up. Next, we will have, sorry, you have to shift the schedule a little. So when this, right, and which way you are? So, Mark Carlson, my good friend, just said that he brought some beer if somebody wants that, because upstairs the beer is open, so round of applause for Mark. So you guys, while you're setting it up.
Yeah.
Okay.
Yeah.
Just one thing I forgot to mention is that all the presentations and the sessions are live broadcast right now to YouTube channel, as well as later on you can watch. And also all of the presentations, I will post them on the storage wiki site. So if you look into the wiki site tonight, most probably they're all open. With that, thank you very much.
Okay. I have one more reviews, so I can read very short slides, so you can quickly get check out. I'm Wes. I'm from Library. So Library is a China-based company. So we are doing some new type of batch storage. So we call it S5. So it's based on redesign story architecture and redesign hardware. In the last 2 days, we see a lot of innovations in hard disk-based solutions, like Mike just presented, and also some software-related, like speed and like stack-based secret. So I'm bringing something new to OCP today. So people go through our solution of S5. It's a general cloud computing architecture, infrastructure architecture. So in last about 8 years, the cloud computing keep evolving. So it started from server virtualization, and several years ago, the software-defined network to get the virtual private network in a cloud data center. And let's share just some idea on the software-defined storage. I think the target of software-defined storage is to build virtual private storage in a cloud data center for different tenants. For example, for public cloud, the tenants may be companies, and for the private cloud, maybe different kind of partners. So that really kind of what we are doing as 5 types for the software-defined storage. So when think about the software-defined storage, and also for definitions. So this is mine. So I think firstly, IOPS matters. So in the hard disk era of storage, for storage, the IOPS cannot predictable because it's disk-based, and for random IO you never know what's the performance. But in the currently in the net flash storage era, flash you can know each disk, each SSD, each flash, how much performance you can get. So firstly, I think IOPS is very important for software-defined storage. Also, we can see from Amazon AWS. It's copied from Amazon AWS website. There's for they call it EBS provision IOPS. It's a block storage for some key application like the RDBS or low cycle database. So each provision IOPS you need to pay about 65 cents. So it's very expensive, I think. Just imagine if you every one application every day have 1 million IOPS, 1 million read write, then you need to pay 65K US dollar just for this storage access. So you can see the provision IOPS is very valuable for this cloud computing. So since IOPS are valuable, right? So for also capacity, also you need to pay for capacity. So we already have same provision function for capacity. So how about the same provision of IOPS? Okay. So think about this. In cloud infrastructure, you have several tenants, and each tenant may have different requirements on IOPS and SLA. Right. So I make an example. For tenants A, there maybe each one have very dedicated IOPS requirements. But for tenant B, they may have very long key application. They need a very high IOPS. The 1 and but for 1, 2, 1, 3, 1, 4, don't care about. You just give a group of IOPS and then it's okay. They don't care about 1, 2, 1, 3, 1, 4, which one get more, which one get less. So it's a one group level storage provision. Also, we can see the whole applications. I just give a like 50,000 IOPS, and each one is depends on itself. Or the tenants, it can himself to define each one is IOPS. So it's like a tenant level provision. So I think, and also you can different level of SLA like gold, silver, and gold level. So it means how long times, how accurate and how consistent the performance it can reach. So this is what I think is important for software-defined storage for cloud computing. And then we back to the architecture of the cloud infrastructure. So currently we already have server virtualization and SDN. So for SDCs or cloud compute for server virtualization, we can allocate VM instance to different servers. And allocation resource like how many CPUs, Q cost, 4 cost, how big the memory size, 1 GB, 2 GB like that. And for example, we can, and also it supports migration. It depends on the data center, the resource usage, and you can easily migrate one web to the other. So it already have SDC and SDN, so how about SDS? So for storage service, I think it's very important. So this one we are trying to do is leverage S5. So it's an S5 controller dedicated for the storage. So it's like, I think it's a kind of similar to server side. So in the computer side, you are composing the CPU and the memory for each VM instance. And as for storage side, you are composing the IOPS capacity for warning or for VM instance or VM group for tenant. So this is also you need an SDS allocate to migrate from different controller. So for example, you can start a application maybe today, and the cloud orchestration, the allocate the VM to server 1 and the storage to this one, and then close today, and then tomorrow I restart it. So maybe tomorrow the VM is in different server, and also your storage is in different controller. So I think it's like for storage side, it's similar to compute side. It's like a service. It's a computer service or a storage. So for S5 controller is the key of what we are trying to do for this SDS solution. So what's the S5 controller? It's a totally reviewed server box. So you compose of it's a three rack view, 20-inch rack, and it can support up to 480 terabytes raw RAM flash. And connect to servers using the 1640G network. And what's the most important, as I said, IOPS is variable. So our current workforce, we can support up to 8 million IOPS in 8K by random rewrite situation, and also at a very low latency. And also the VM tenant step QS and the very good SLA, and also scale. So this is what we are trying to build in last 2 years, and now we are bringing to OCP. So how we have a lot of discussion in the booth with a lot of companies, how we reach it. So firstly, we think on the system architecture. It's a typical x86-based architecture. So we have a CPU, DRAM, and and have a speech next to NIC network interface controller, and also to store and meet either HDD or SSD. So in old days, for hard disk solution, I think it's okay, it works fine, because hard disk is the IOPS is more, and it's very good at only at the sequential rewrite block, big block read write. So, but when we think about IOPS, then the storage, and for flash, then the CPU can work back. So I have so everybody knows that previously flash is enclosed in a SATA interface, and now changed to PCIe. Okay, so using PCIe interface, the flash performance IOPS can burst out. So for each PCIe SSD, you can reach about 500,000 of IOPS. So 500,000 IOPS, even the most new Xeon processor, you can only support 2 or 3. But when we think about the box, we have maybe tens or more. This is kind of flash piece. So it's about 5 million or 4 million or 10 million or even 100 million of IOPS. Then the PCIe fabric and the CPU becomes the bottleneck. Okay. So I think so for this flash-based storage solution, and when we want to think about to solve the IOPS is vulnerable, remember it. So then the CPU and the system architecture, especially the PCIe fabric, becomes the bottleneck. And also the software-based, like EMC used to do, restrict the consistent QoS. As I said, when the QoS, the IOPS is very low, like 100K level, is easy to ensure the consistent QoS. But when you run to each virtual machine, each volume can have 10K, 20K, even 100K IOPS, then the QoS is on software. So a lot of people, a lot of the engineers see this issue, and I see a lot of kind of improvement. So it's an example on the improvement. It came from DSSD's solution. DSSD sold to EMC last year. So they can modify the system data flow, but still this kind of system, similar system architecture. So they leverage the PCIe's which multitask function. The first from data from NIC go to DRAM, the CPU tell the PCIe switch data should to go to storage media, which is or which SSD, and then from the NIC goes directly to DRAM in the storage media. So it's also kind of leverage the PCIe multitask function and also trying to do it to release CPU from the data flow. So for the third step, it needed CPU involvement. But it also still have some limitations. So for example, the PCIe switch, you still need the multitask and the PCIe switch performance. It's a multitask situation is slow. And also, for this kind of solution, there's a low data processing support, like a RAID, because the NIC cannot do RAID, and a lot cannot do queue. So it goes to the CPU for the data service application. So when we think about this, we can do such small improvement to get higher IOPS, but still it's for the right one, I think. So when it's just like similarly. Previously, we think SATA is not designed for flash, right? So we changed to PCIe, and then now use the MME step. But we think one more step. PCIe actually is not designed for flash. Only when the PCIe standard 1.0 7 years ago, there's no think on how to support NAND flash. NAND flash and they have a lot of legacy issues. So on this, we proposed a new architecture. So we call ExpressQ. Firstly, we eliminate the CPU from data part. So we can get a very higher out, just very straightforward data flow from NIC to each flash port. Secondly, we support the ASIC-based parallel queue to ensure the QoS for the volumes of tenants. And also we eliminate PCIe fabric. So it's like a network attached device, you cannot attach it more as possible. You get a very high flash density. So in detail, it's like this one. So we are using enhanced big controller. So it's like this one. You can find my okay. 4 by 40 GE and all accelerate. And then we review the, let's say, the switch fabric. So this low PCIe inside. So it's called double X switch. It's distributed, so we have 30 switch fabric adapted in a box, inside a box. And then also the flash side, the aggregate 68 terabyte flash adapter as a flash core. So this is our new architecture. So based on this one, new things, and also we designed the hardware. It's composed of the current one is composed of 4 network peak adapter and 30 switch fabric and 60 flash core. So based on this one, we can get 8 million ions per box, and it is scalable and very consistent and accurate QoS storage. That brings the OCP. So we are using OCP stuff from the sustainability company. Then a lot from here and decided to contribute everything, the architecture, the files, everything on the box. So we are also trying using this first format platform. So we have some in the 3.0 version already done, and we have 1.5 version in the April like that. As shown is a new kind of storage architecture, low PCIe fabric, low x86, doesn't matter. So, and we want to get more partners on ODM system, software-defined storage, and solution provide join and together to develop a new standard, new kind of storage solution for flash. Also, we are doing a lot of assistance on OCP kind of operation. So for more details, you may visit us at booth E15 or send an email. Thank you very much.
So, thank you very much, Vince, again. Oh, you have all this questions. I forgot Henry's in the room.
You should have one. I think has anybody gotten through without a question? In fact, since this is also a server change architecture, this should also be submitted as Honey Badger was into both the storage and the server working group. Version 1, the BMCs worked out all of that. So I encourage you to resubmit as well to the server group.
Okay, thanks. That was good.
I just question about the QoS.
Yeah.
In multi-tenant environment, can you throttle tenants in a multi-tenant environment QoS? So if I think I saw on one of the slides that restrict tenants based on QoS.
Yes.
But if they're not restricted, can you throttle them based on maybe some parameters that you preset?
So you mean about the tenants level QoS? So I said it's pretty proposed cloud data center architecture. So for example, for one VM and so you can its storage access and we are as S5 controller. So also you can for tenants you may have hundreds or thousands of virtual machines and have similar volume count. So it's running maybe in different servers, but you just allocate all these volumes to store this to one S5 controller. Then you can get tenants level address. So you have a restriction, so you should put all the access to one S5 controller for all the warnings. But as I said, each S5 controller you can reach 8 million hours. So I think it's enough for tenants of a group of one. So we have maybe different servers, but you all the storage provision to S5 controller, and then you can get a group on tenants address.
Other question. The express fabric here. The express fabric based on implementation on ACC.
Currently, it's based on FPGA. So yeah, we have some all these connected to OCP. We can modify them.
Again, all the slides will be posted to the storage website. If there is no more.
Quick question. So is your DIM, if a DIM fell, what is the serviceability here? What is the serviceability of all the hardware? The NAND fell.
NAND flash, yeah, it's also swap. You need to power it on top of it, remove the cover and then swap.
So the data is.
It's just like a disk. You can remove and auto refill that.
Okay, so is there some kind of redundancy?
Yeah. Already, we currently our current putting the range inside box for different flash.
So, is there any more questions?
What is the interface of the flash module?
Can you repeat the
Flash
question?
module.
What is the interface of the flash module, please?
Currently is next is a PCIe similar and float point package. Yeah, we are inside this box. You need a float, and as I said, it also have a lot of complexity on PCIe. So we use a even simple protocol rather than like MME. Yeah. For each flash package.
All right, so one round of applause again. Thank you very much. And our next speaker is Rob. Rob, you ready?
We have the first speech.
All right, great. So thanks to Mark and Pat for our bartenders tonight. Work on it.
I'm gonna make a run.
Yeah, because I felt like I was kind of cutting into the beer conversation. All right, so I'm going to talk about a fun little project called Igloo. The cold storage concept. I want to keep data around for a long time and not have to pay a whole lot for it, not have to burn a lot of power on it. And I'm in a new group at WB called WB Labs. So it's a kind of a new place where we get to go and play around and do some kind of interesting and different things, and try them out and see if they work. So this is definitely a work in progress, just trying to understand if we can get away with this kind of thing. So the first concept is what is cold storage, how does that work? And so for some people, they'll keep 3 replicas of data, and they'll take those replicas and do I need all 3 of them, or if I have 4 replicas, do I need all 4 of them? And I push them in the cold. And I'll cut it up into little shards, I guess, from the erasure coding. So we'll erasure code these things and store them away for safekeeping. If the 2 hot copies ever fail at the same time, oh my gosh, well, we got to go back and rebuild. One somewhat available, so we could do that, but it's a really rare thing. So that's one. The other one is you got your RAID system, right? This really nice precision RAID machine, all parity striped, beautiful. But eventually the data on there gets cold too, so do you want to keep that big hot RAID running? No, we want to push it off onto cold storage. And finally, there's even guys doing the local erasure codes and things like that, running stuff erasure coded already, but it's hot on an expensive machine. Let's push it into a low power system and put it aside. And so again, this is stuff that you don't want to use anymore. You want to keep it away, but you got to keep it. So what would that look like? So in here, I kind of built this is like a triple rack, divided up into different power zones. And the hot zones are colored, the rest of it's powered off. So on the one hand, you get write instantly in this system. You can always write to one of those stripes that's powered up. So you always have availability to write right away. Boom. On the read side, it's kind of a read seldom use case. Did I have both things fail at the same time? Oh my gosh, I gotta go read it. So it's fairly rare. You look at Amazon Glacier has a SLA that you can read online, and that's like you write all the time, but you need your data back. It's a 2.5 hour thing after you submit a job request, they'll give you your data back. So 2.5 to 5 hours or something like that. But it's a very long time to get your data back, but you will get it. So this is the kind of use case that you're thinking about. And there's a couple ways of doing it. So one way within those power zones is kind of a ring where you'll arrange power zones in that stack and move through it. And you can do just a predictable 7 to 10-minute stops. And so your average read latency is going to be 75 minutes, how long it takes to get halfway around that loop on the average. So this is it's very easy, very predictable, and it works. Another one, and there's a paper Microsoft published in the summer, Pelican. Really cool, taking the same concept of very unprovisioned, very low power system, but now queue up your data requests, like you queue seeks today in the drive, you now queue up spin-ups instead of seeks. And so they do this little rather salesman gets you your data actually in a few minutes, depending on workload, on how heavy the thing's loaded. So that's another more sophisticated way of doing it, and it gives you a different, you're spinning the drives up and down more often, but you're getting your data faster. So depends on what you're after. So how do we build this thing? So if we build up this rack, three racks, we ended up with 1,800 drives in it and 10.8 petabytes, 6 terabyte drives. And there's 120 drives actually active in that thing. And the way that I think I can put this thing together, I'm only going to burn 1,200 watts in that triple rack, which is really, really fun and low. So again, there's 6 power groups. Each of the groups, the way I drew it here, there's 20 trays in that set of groups. 21 group. And within each of those, it's based on an OCP chassis, a Knox, right? There's 15 drives, and we'll just step through those
those drives. One of the fun things you'll do is stagger, so you're not going to switch through all 6 of them at once. You're going to switch just one at a time, so you got 5 that are still up and running. You got definitely a wait time while you're spinning up the next group, powering up the last one. And in this case here, I put 20 drives high, saying, okay, here's our group of 20 drives. I can do erasure coding if I'm doing an 18 drive or a code stripe or a 15 drive stripe. I got plenty of extra over provision space. And the last point, kind of a fun point, if you actually put this in a real data set, you won't put them in neat rows like that, because if that one rack goes, you've lost all your data until that rack comes back up. So you'd actually scatter this and have an algorithm that scatters it real nicely. So you can blow up a rack and still get all the other data back from other racks. So how is this put together? How do you actually build it? So here's my set of racks, and traditionally you'll have a client out there that's trying to store the data. Top rack switch the data goes through, and then you have servers, HBAs, expanders, and then you have SATA drives below that. That's how you typically build up these racks. So instead, the concept here was, well, we're going to make these storage trays, and the storage tray actually is a bunch of HDAs, and there's only one set of electronics for the whole tray. And so now I don't have an expander card. I don't have all that extra effort going into breaking the data out and pulling it back into the drive that happens to be active. So it's a very lightweight system. And when you look at the power consumption in there, I'm only at like 0.13 watts per terabyte. It's a really, really low number. Get that down to 0.13 compared to what we were, 0.62 watts if I had 6 terabyte drives in the other example. So I get a really neat power savings by throwing away a whole bunch of stuff. So again, here's how we build it. We've got our HDA, we've got the PC board that sits on top of it. Some NAS hardware thrown around. So there's a CPU on there, runs Linux, hooks up to the network directly. And then we need some electronics to mux that out to 15 HDAs. So that's the extent of the electronics for this big tray of active drives. So this was the concept that started out. We started drawing up sketches. Said, okay, well here, let's make a circuit board. We'll put these boards on there. We'll throw some sheet metal around it. And when this thing's active and running, it's pulling 10 watts. It's 6 watts for the drive, 3 watts for that network attached storage piece. And then this is actual drawings. We got into getting a real schematic going, getting the board going, kind of showing the state where we are. So this is the layout. It's in progress. This thing isn't real yet. We're testing. But I'm getting to talk to you guys early on. So this is the footprint underneath one HDA. Basically, there's a power chip there to spin the motor, and the sensors, so the shock and wrap work out, so your vibe problems are all taken care of. The drive works just like a normal drive. Spindle connector and the HDA connector. So pretty lightweight. And then when you look at the whole board, this is the full layout. In the center, there's one SoC, and the rest are just the PLSI chips. And there's four MUX chips there, FPGAs, to make this happen. It's a cell phone parts for high-speed stuff for the preamp. And a little tab that sticks out the bottom. I'm not sure we hook up to other stuff outside this cluster. And then that's also tied into this little, first one we'll try out is this little Minnow board. It's a little Intel Bay Trail dual core. Pretty much like the baby honey badger that they were talking about earlier. This is about what this little board is. It's Ethernet out the end of it. We also, if we actually put this on the main board, if it works out and everybody loves it, we can put dual port Ethernet on there so you don't worry about you have redundancy. Right? Another question. So, you got all this power consumption. What's the thermal really look like? So if you look at an HDD, it's got about an hour time constant. I'm turning them on for 10 minutes. They're really not getting up to full operating temp. So they're on 7% of the time, maybe. So they're going to stay kind of cool. And think about, okay, this is a 1U pizza box kind of size thing. It's dumping 10 watts. Do I need a fan? People kind of freak out when I say that, but I don't know that I need a fan.
Not Apple.
But yeah, they would like it without fans. And so I did a quick napkin calc, go to Google, pull down the equations, right? And I got two plates the size of a 1U, the front and the back of a 1U rack. And if you make that a sheet of aluminum and you put 10 watts into it, with that surface area, you're going to get about a 10 degree C rise. So, that seems not too bad. I could probably get away with it. So that's what I'm hoping for. And here's kind of a map showing where the HDAs sit, the average power in each HDA, the SoC 2 watts in the middle. It kind of got cut off, but anyway, there's 3 watts there for the CPU card, and then on the other side, they're half a watt for the 12.5 volt converter, with its efficiency of 90%, or say 5 watts. So anyway, seems like it doesn't get too hot and should be okay. So I'm really hopeful. If not, we throw bands on it. So kind of to Q&A for you guys. How many people here in the room, just raise your hands, actually work in cold storage areas or need cold storage? I think it would be a cool thing to have. So we've got a couple people. I know the rest of us are probably all drive makers, but
It's only 3.
okay, there you go. So yeah, so
according to him,
pretend, yeah. I do pretend. So that's good. And so I mean, does it look interesting? And does this look like an easy to use box?
Well, so my question was, first of all, when you talk about accessing this, have you built any sort of protocol layer that might be talk to this thing?
So,
that is recognized.
So one of the things we've done at the moment, we did tie a whole bunch of drives to a whole bunch of boards similar to that, and we loaded Ceph on each one of those modules, and so they work together as nice little clusters. So you can erase your code with each module doing the sharding for you. So we have done that. I haven't dug deeper into what's the best cold storage, because no one really has, I got the best cold storage. A lot of companies, yeah.
Realistically, you can do it later,
Like S3, yeah.
What I would be concerned about is the reliability of the drive. Certainly, back to the
yes.
we're talking about what drives really this like is being out of their butter zone, out of that zone where they like to operate. You're going to have a bunch of easy ones. You're going to drive nowhere near that butter zone. They're going to be warm, but never cold. So I'd be concerned about the reliability of the drive.
Okay.
Can you
Yeah,
repeat
no,
the question? Repeat the question, we couldn't hear.
Oh, okay, so he's asking about reliability.
So
That's
Yeah,
even
there
better.
you go.
Thanks.
As the gentleman from Seagate pointed out, when drives are too cold and they're operating, they're unreliable. And we all know that when they get too hot and they're operating, they're unreliable. This system would have the drives being just warm all the time. And I would be concerned, I would be interested to see if you guys have any modeling or anything that can show what the reliability, the expected reliability is. But I think it's a great concept.
Yeah, both extremes are bad, and I know keeping it like 40 degrees C is just like awesome. If you keep it there, that's great. But I don't. The other thing, one of the things that was cool about what he talked about is actually checking these things for reliability, and then actually using a drive, even if it's partially not there, continuing to use it. And that's kind of the premise of this, where these things are screwed in, bolted down. You're servicing them as a rack unit. But I wanted to degrade very gracefully so we understand what's failing and only take off the little bits that are failing, and not, oh, let's throw the drive away.
So, Rob, before the next question, are we in the question session or are you coming?
Yeah, this is basically it.
Is that okay? Okay.
That's it. So,
We have a question.
yeah. Thank you. WD Labs. So go ahead.
Yeah, thank you. So you threw out the word archive. So when I hear archive, I immediately start thinking tape and optics, which are government approved archive, 30 years and things like that. Are you are you thinking of targeting that kind of length of archival, or are you still thinking 3-5 year warranty timeframes, hard drives, or?
Yeah, so that's a great question, and I don't have the answer. I am, have lots of thoughts about it. It's still based on a hard drive, and today hard drives are 3 and 5 year warranties. So that's work for me to do in our company is how do I push that and I get it out to 7 years or 8 years or 10 years. I don't know if we're gonna have a hard drive that's a 30-year lifespan. So, I certainly think there's a lot of use if we can push it, make it a useful 7-year retention, for instance.